Please turn to page 476, problem 9.17. We are given a 50 volt voltage generator which operating at 20 megahertz frequency, and it is connected to the parallel plate capacitor as shown here. And then we also given the area of the plate given as 2.8 centimeter squared, and also it has a distance of separation between the two plates as shown here is equal to 0.2 millimeter. Okay, so now we are going to find the maximum value of displacement current density, the JD, as well as the displacement current, the ID. Okay, so now guys, so since we have these informations of the voltage generator, so we can simply find or have our equation for the time varying voltage, right? So let's say we choose the cosine waveform. So now we're going to have 50 cos 2 pi times the frequency equal to 20 times power of 6 t volt. Okay, so that's our time varying voltage generator, and now we are going to find the JD. So as we learned previously, the JD can be found using these equations: dd over dt, or equal to epsilon dE over dt. Okay, since we are given the delta between these plates actually is filled by the air, right, the free space, so we can simply have here epsilon naught. Here is our air, epsilon naught. So now just differentiate the E over T. Alright, however guys, we don't have the E yet, so we just find the E from the VT. So practically we will see that there is the fringing effect that appear around the edge of the capacitor, right? That's in practical, right? Normally we have this one that's called a fringing effect, right? However, if we use a very large area of plate compared to the distance of separations, we will not see this effect quite significant, so we can simply ignore the effect, right? That only applicable when we have used the area of the plate that much larger than distance of separations. Then we can simply ignore the fringing effect that normally appear at the edge of the parallel plate capacitor. Okay, so in that case, since we have assumed that we ignore this effect, so by right the E will go in straight line, or will have a uniform E field across the capacitor. Alright, so since we have assumed that the E field now becoming uniform field, so we can simply find the E field that uniform by dividing the VD over the distance of separations. Okay, so that's the idea. So now let's put in the value of VT. Now we have a 50 cos 2 pi times 20 times 10 power of 6 t over 0.2 milli. Okay guys, so you have the E field finally, time varying E field, which equal to 0.25 times 10 power of 6 cos 2 pi times 20 times 10 power of 6 t T. So if you assume that this plate is positioned along the y-axis as shown here, so you can simply have here in positive y directions, and for sure it has unit of volt per meter. Alright, so that's our E. So now let's differentiate the E over T to get the JD as shown up here. So now to have a JD, we have here the epsilon. Now we have here 0.25, the peak of the E field, times 10 power of 6. Now differentiate over T, gonna have here negative 2 pi times 20 times 10 power of 6. Right, now we have sine 2 pi times 20 times 10 power of 6 T. Okay guys, so if we proceed, you will have the value of JD, right, which will equal to a negative 278.16 sine 2 pi times 20 times 10 power of 6 T. And also it must have same directions in y directions, and now it has unit of ampere per meter squared. Okay guys, that's our complete equations of the JD. So from that we can simply find our maximum value of JD. So the JD maximum value is equal to 278.16 ampere per meter squared. Okay, so lastly we are going to find the ID. So the ID, as we discussed previously, can be simply found by applying integrations jd.ds. So the ID integrations jd.ds, right, the ds here given as 2.8 times 10 power of minus 4 meters squared. So just times the whole term here with 2.8 times 10 power of minus 4 to get the value of ID. So now we have negative 278.16 sine, let's say you just put omega t to make it short. Now here y component, a dot vy as well, a ds. So the ID here we're gonna have, which equal to, let's calculate together the ID. Let me find my calculator. Okay, 278.16 times 2.8 of minus 4. We are going to have this value 77.88, right? Negative 77.88 sine 2 pi times 20 times 10 power of 6 T. Okay, now it has unit of milliampere. Alright, so again, that's going to be our maximum value of ID. The ID max will be equal to 77.88 milliampere. Alright guys, so I hope you can try yourself, and all the best for your study. Thank you.